This is AP Calculus AB. We're on notes 11-3 for volumes of square cross-sections. Our objective today is to find the volumes of shapes with square cross-sections. So this is the first lesson that we're actually talking about volume. If we've mastered areas, specifically areas between two different regions from 11-2, then we can extend those areas into the third dimension with a bunch of different types of shapes. So this is the general path, and this path will lead you to the correct answer. We're only going to be focusing on the path with the squares, but I'm letting you know there are many other paths that are open to us. I'm only going to be focusing on squares in this lesson. In general, you start off by looking at some area that it will define for you. So I've taken this area and I have dropped it onto this XY plane, and this Z is coming out of the paper. And then you can choose any cross-section you want. You can choose a cross-section here, here, at the very tip down here. I just randomly chose the center. And then typically this cross-section is perpendicular to the x-axis, although it could be a cross-section that's perpendicular to the y-axis. So instead of drawing the line like this, I could be drawing the line like this so that it would cross that y-axis. But generally, they're always going to be like this. And then it will ask you to pop that shape up into the third dimension by making a certain shape. So from this line, we're going to pop this shape up to make a square. But you could make an equilateral triangle. You could make a semicircle. Again, remember that word semicircle literally means half of a circle. It doesn't mean like 60% possibly of a circle. It's exactly half of a circle. It could be a rectangle. It could be a bunch of different shapes that you might see. Most typical on the AP calculus test is to see a square. So, and you need to make sure that that square has one side on that original cross section that you drew. And because it's a square, we know how to find the length from here to here. It's the top function minus the bottom function will give us this length. And then this length is the same as this length, which is the same as this length, which is the same as this length. It is a square, and to find the area of that square, I can just do base times height, and then you can integrate. So finding the area of the shape for a square is really easy. It's just that base times the height. Although finding the area of a different shape could be a little bit trickier, because if you only know this length, it's a little bit hard to find the area of a triangle. If I only know this length, it's a little bit easier than a triangle to find the area of a semicircle. But you essentially find the area and then you integrate. So to demonstrate what's going on here, I'm going to, I mean, these pictures are lovely, but even better than that is a GeoGebra applet that I did not make. Someone else made this for me. So this is linked to in the notes, but essentially I want to show you this on the right is just a 3D area that I can look at, and I can choose any sort of type of cross section that I want. So if I want it to be a square, you can see that if the square is drawn in the center of the cross section, it can change depending on where I draw that square. If it's over to the far right, it's a very tiny square, or it's over to the very left, it's a very tiny square. What essentially we're doing is we're choosing that to be the cross section, and then we're creating a bunch of squares. So if I have a few squares, you can see, I don't want to do that. You can see the more squares that I have, this eventually turns into a volume. Once I have an infinite number of squares, that volume is what we're essentially being asked to find. You can see that this volume is a little bit different than if I do a slightly different cross section. So that's a square cross section. But if I turn that off and do something like an equilateral triangle, and I can, again, choose that equilateral triangle to be wherever I want, and then the more equilateral triangles that I have, the more you can see that that shape is defined slightly differently than if those triangles had been squares. All right, and then what happens if we had that cross section be a semicircle? It would be a semicircle like this. Again, you can see the size of the semicircle depending on where that function is defined for the cross section. And then once I have a certain number of semicircles, I can see that that shape eventually turns into something that looks like this. Kind of cool to see that shape in the third dimension. If you want to play around with it, there is a link to the notes where you can see it as well. But we're going to come back here to the notes. That link is right here. So let's go ahead and jump into an actual problem where we're going to find this. And I'm showing you one picture here, but never again. Usually you're only going to see an area like this, and you have to find that volume. So let's just read in the figure below. R is the shaded region right there, and it's bounded between two functions, a top function of natural log of x plus 1 and a bottom function of x squared minus x. And it forms the base of a solid. And for this solid, each cross section, which is perpendicular to the x-axis, it'll always say cross section. It'll always be perpendicular. Typically, it's going to be perpendicular to the x-axis, meaning that we draw a line that looks like this. We say, okay, we're drawing this vertical line because that's perpendicular to this x-axis. It makes a 90-degree angle with the x-axis. And then it's going to be a square. So from that line, I draw, and it's fun to draw these. You can say, okay, this pops out into the third dimension. So this is how I'm choosing to I want that to be a curve. I'm choosing to say this comes out into the third dimension. right about there, I think. And then I can connect these two. Okay, I didn't do the best job there as a square, but there it is. There's the cross section, and then it pops out, and then there's a square. This is what the actual picture should look like. It's an infinite number of these squares happening, and we need to find the volume of that solid. So again, I'm kind of doing these steps. I made the cross section, I made the indicated shape, and now I'm going to find the area of that shape. So the area of this shape here is what I'm after. And you only have to do this once, and then it's just a general formula that you can memorize. But essentially, I have this square. This square right here is this square right there. I can draw it better right here. So how do I find the area of this square? Let's go ahead and say that I'm going to make this bottom length right here. Let's make that a blue squiggle. This is my blue squiggle. So that's the bottom of the square. What is the length of that bottom of the square? Well, it's the top minus the bottom. The top function is natural log of x plus 1. The bottom function is x squared minus x. It's a little bit tedious to say, and since I have access to a calculator, I'm just going to call top is f, bottom is g. So this length right here, this length is f of x minus g of x. It's always top minus bottom. That is the definition of this length. And notice that this definition that I've given for this length is the same definition for that length, or that length, or that length. It doesn't matter which cross section I choose. It'll always be top minus bottom. If this length is top minus bottom, then this length right here, I should do this in pen, this length right here is also that top f of x minus the bottom g of x. And we're going to find its area. And again, I know that I put a little asterisk here. I'll talk about why there's an asterisk on the word area, but I'm finding the area of this square, and that area is these two lengths multiplied together. So I'm going to say the area is f of x minus g of x times, so I can say all of this, times the other f of x minus g of x. That is exactly the area. And it's a little bit tedious to write this out twice. Since I'm multiplying this, I can say that there's really two of them, and I can simplify this to say it's really just f of x minus g of x, that entire quantity squared, because there's two of those terms. This is the area. Notice that I've accomplished this, find the area of the shape, and what's left to do is I just integrate. I'm done. I just slap on an integral symbol. So I can say it's the integral of those, and then with the correct bounds. So the bounds are going to be whatever the original bounds of my area were. My area went from 0 to, I'm not sure. let's go ahead and find it, right? So what I'm doing here is I'm saying I don't know this, this x coordinate, but I can find it. Right now it's a question mark. I need to use my calculator. That's why it is a calculator question, right? So let's go ahead and actually I want that open. And I'm just going to slide you over to the left for a sec. Let's open up our calculator. I had some other stuff going on here. So let's go ahead and do a second plus. We're doing a memory clear, so 712. Memory has been reset. I'm going to change the mode so it's running to 3 decimal places, and I'm ready to go. Calculator is nice and small. So I'm going to graph these two shapes. I'm going to say my y equal to, I'm going to come up here and say that this is the natural log of x plus 1, and my other function is going to be this x squared minus x. And you can see the window here, my x coordinate goes between 0 and 2. So for my window, I'm going to say that my x min goes from 0, and my x max goes to 2. And I have the y scaling. I don't need a zoom 0 this one. My y scaling is from 0 to 1, or actually negative a half to 1. So negative 0.5 to 1. And I can graph that thing, and oh, there it is. I'm going to find where that intersection is by doing a second trace, do a calculation of the intersection. So I'm going to hit option 5, and then follow the prompts. I think my prompts are a little bit different than yours. My is asking for my left bound, so I'll say, I don't know, 1. And my right bound, I'm just going to say 2. And it says that intersection happens, I'm going to write this down here in my notes, is going to be 1.59, that 7 is going to be rounded up to an 8, 1.598. So that means that my integration over here is going to go between the bounds of 0 to 1.5, that's supposed to be a 598. And don't forget your little tiny dx. And this dx, I can actually explain where it comes from. We'll do it on the back side to explain where it comes from. So we're done. I can just type this into the calculator now, and it's ready to go. So let's go ahead and get out of this. So second mode to quit out of this. I'm going to do math 9, and my bounds are 0 to 1.598. And I'm going to come over here and say it's f of x. Is that my y1? F of x is natural log. Yeah, okay, so it's my y1. I just want to double check that to make sure that I get this correct. Oh, kind of a funny thing here. Because this thing is being squared, if this were a negative answer, you're going to square it and it's going to go away. These don't actually matter. I could have done g of x minus f of x, and I would have gotten full points on any AP test, and my calculator will even tell me I got it right. It doesn't really matter because I'm squaring it. Although if I had some other area like maybe a semicircle, then it kind of matters because maybe it wouldn't get squared. Actually, circles are squared too. Triangles are not squared. Then I'd have to be careful there, right? Anyway, let's come out of here. And then I'm going to say it's going to be the quantity of, so I'm starting extra parentheses. I'm going to say alpha trace y1 minus alpha trace. I'm going to scroll over here to y2 and hit enter. And then I'm going to end the parentheses, and then I'm going to say that is going to be squared. And then I hit enter. And my answer here, this is equal to 0.479, 0.479, and that's the volume. It was a very tiny volume. The shape was very small, and then just extending it out a little bit doesn't give it that much. So it does make sense that this is such a small volume. All right, well, that's our first example. Let's try another, shall we? Oh, before we talk about the example two, I want to talk about where this dx came from. Why do we have a dx there? And what's the generalized formula for any square? So I can generalize this to say, hey, if we say that we're going to assume that this wavy blue line right down here is that bottom of the cross section, so it's that same wavy blue line right here, we're going to assume that it's always going to be the top function minus the bottom function. Again, sometimes it's like a curve that looks like this and like this, where you have to split the function. Maybe it's a left function and a right function. It doesn't really matter how you find that function, but it's whatever that length is. Typically, like I say, like 95% of the time, it's always the top minus bottom, but sometimes it could be different. Generally speaking, this is always going to be top minus bottom. So this length right here is going to be defined as top minus bottom, and therefore, because it's a square, this length, and I want to be very specific here, I'm talking about this point, not this point. So I'm talking about from here to here. That is also going to be top minus bottom, which means the area of the square, like let's assume that we have the correct bounds for our area, is always going to be top minus the bottom quantity squared. And then again, I should talk about where the dx comes from right now. That is the Spicci definition of what is the area of a cross-section, or the area, I should say, this is the volume actually. What is the volume of a cross-section with squares? This is 100% always going to be the formula. So why the dx? Because technically, and this is where we get into the more of the philosophy of calculus that you don't really need for the AP calculus test, but since I'm here, it only takes a few minutes. Technically, we're really finding volume. This, I kind of did some hand wavy saying like, that's really area. This is volume. I'm addressing this asterisk right now. Technically, what I should say here is this is, I can spell volume. We're really finding the volume of the shape, because the volume is defined as this area of the square, and then we extend it out a little bit to make it volume. This measurement, and I can talk about this right here, this measurement right there, this measurement right there is technically dx thick. That is the size of this. And because dx basically goes to infinity, or I guess it doesn't go to, dx goes to 0, and you're counting an infinite number of these slices get so thin that you can calculate this perfectly. That's the philosophy of calculus. So really it's top minus bottom times top minus bottom times this thickness dx. So there's 2 dimensions here, the 3rd dimension here, and these 3 dimensions all multiply to a volume. All right. So if you prefer, we can also say that I don't think this is going to be the Spicci definition, but some people prefer f of x to always be the top function and g of x to always be the bottom function. You could say it's this thing, quantity squared dx as well. I prefer this one because it makes more sense to me. All right. Finally, we'll do a second example and we'll call it done for the notes. Again, we're going to be using a calculator. It's the same thing. I'm going to be giving you square cross sections on all the homework assignments, so you don't need to calculate any other shape. So I have square cross sections, and what are we perpendicular to? We're perpendicular to the x-axis. So if we're perpendicular to the x-axis, which I think all the homework problems are as well, we'll see here in a bit, this line right here is vertical. It is perpendicular to the the x-axis. There's the word I'm looking for. I'm going to pop this out into the third dimension. Does that look, oh, that looks terrible. Like that. There we go. And then maybe if I just copy and paste that line, there's a good idea. So if I copy and paste that same line and I just put it over here using technology, I think that's right about right. A little bit farther right there. And then I can just draw a line right there. Oh, look how fancy that looks. Technically, there's a 90-degree angle right there, right? It's a cross section that comes out into the third dimension. We can say that that is a square, and there's like maybe a tiny little square right there that pops out right there. There's an infinite number of these squares if I draw a bunch of these tiny little cross sections. Anyway, that one cross section, we can skip going in and finding the area of that square, because I know the area of the square for my speed sheet. It's just top minus bottom square, and I can just plug it straight into the integral. The integral is always going to be, I'm going to come down here, the integral is always going to be top, which is going to be f of x in this case, minus the bottom, which happens to be g of x also in this case, and I do that quantity squared dx. It's ready to go. The only thing that I'm missing now is the bounds. What is this intersection? What is this intersection? If I find those two intersections, I am done. So what's that thing? What's that thing right there? And what is this x coordinate over here? Once we get these x coordinates done, we're ready to go. So I need to graph these things. So on my graphing calculator, I'm going to come over here. Let's clear out of both these functions. Say my y1 is my f of x function, so it's going to be a second natural log, so it's an e to the power of negative x squared, and my y2 function is my x squared plus x minus 1. Oop, that's a plus, so minus 1. There we go. And I can change my window here very clearly from the graph. I go from -2 to about 1, so I'll say from negative 2 to 1. Feeling lazy. I think I can figure out zoom 0 from there. Zoom 0. Beautiful. Let's clear out of those things. Okay, so I need to find these intersections. So I'm going to do a second trace, and then hit option 5 for an intersect. Just follow the prompts on your calculator. My calculator is asking for my left bound, so I hit -2. My right bound, I'm just going to say -1. And I get this intersection, which I'm going to log over here as -1.647. And then over here, I'm going to do this whole thing again. So let's clear out of this. I'm going to do a second trace to do a calculation of the intersection. So 5, and just follow your prompts. My prompts tell me left bound, which is going to be 0.5, and my right bound is going to be 1. And it's telling me this intersection is going to be 0.825. 825. All right, so we have our bounds. We can come down here and say this goes between -1.647 to 0.825, and we just need to enter this into the calculator. So here you go. Second quit out of this thing. So it's going to be math 9, and it's going to be, oh, do you know what I really could do? I basically need to enter the last line. I might as well hit second enter to enter that second, or that last line anyway. All I need to do here is change the bounds, right? So let's change this to 0.825 and come down here and delete that and change it to -1.647. Y1 and Y2 have been updated since the last time I did this, so it should work, and I get my answer, which I'll write down over here. This is 5.577. Excellent. All right, well, that concludes AP Calculus's AB's notes for 11-3, volumes of square cross sections. Thanks for watching.